Rising out of a limestone plateau on the west bank of the Nile River, the Great Pyramid of Giza stands as a 4,500-year-old engineering anomaly. Despite millennia of storms and shifting civilizations, the structure remains anchored in the Egyptian desert. This chart compares the scale of modern achievements to ancient ones. The Burj Khalifa in Dubai weighs roughly 500,000 tons. The Great Pyramid, by contrast, sits at over 5.75 million tons, roughly 12 times heavier than our tallest modern skyscraper. The construction required 2.3 million blocks of limestone and granite. Many of these stones weigh 80 tons each and were transported to the Giza Plateau from quarries located 800 kilometers away. This overhead map shows how the base aligns to true north, south, east, and west. The builders achieved this orientation with millimeter precision long before the development of the magnetic compass. The interior design also maintains a constant environment. While desert temperatures fluctuate wildly between the sun and the night, the inner chambers remain fixed at 20 degrees Celsius. During the solar equinox, a time-lapse reveals a hidden geometric detail. A subtle inward crease runs down the center of each face, meaning the Great Pyramid actually possesses 8 sides rather than 4. This combination of geographic precision and environmental control, achieved using only copper and stone tools, suggests a level of logistical sophistication that challenges our standard assumptions about ancient labor. The difficulty of explaining these construction methods has led to various fringe theories, including the claim that the pyramid functioned as a piezoelectric power plant. This diagram illustrates the power plant concept. It suggests that the weight of the limestone pressing on quartz-rich granite inside the chambers could generate an electric charge through the piezoelectric effect. These ideas often reference Nikola Tesla, who explored using the Earth's surface to transmit wireless electricity. Some researchers attempt to link Tesla's energy concepts directly to the pyramid's geometry. Other popular interpretations include the ancient aliens theory, which frames the pyramids as navigation markers for deep space travelers. While these science fiction explanations gain significant public attention, the physical evidence of how humans actually moved and raised these stones reveals a more practical, though equally impressive, reality. Reconstructing the construction process requires solving a major logistical hurdle, moving 80-ton blocks across 800 kilometers of terrain without modern machinery. Ancient papyrus records confirm that the Egyptians utilized the Nile River as a heavy lift transport artery, using coordinated boat teams to float stones toward the plateau. The challenge shifted once the stones reached land. Without the use of wheels for heavy transport, the builders had to drag these blocks across dry desert sand. This model demonstrates the physics of dry sand friction. As a sledge moves forward, dry grains accumulate in front of the runners, creating a physical barrier that drastically increases the force required to move the load. Applying a specific amount of water to the sand solves this. The moisture binds the sand particles together, creating a rigid surface that prevents the grains from piling up and reduces the required pulling force by half. Evidence for this technique exists in a wall painting from the tomb of Jehuti-Hotep, which shows a worker pouring liquid directly in front of a sledge being pulled by a large team. Overcoming the desert environment relied on an empirical understanding of friction and fluid dynamics, rather than advanced mechanical tools. After transport, the final task was elevating 5.75 million tons of material to a height of 480 feet. The most common explanation is the external ramp theory, involving a massive slope of mud and brick built against the face of the pyramid to drag the stones upward. This diagram shows the scale required for such a ramp. To maintain a manageable incline for the workers, the ramp would have to extend for over a mile, requiring more material than the pyramid itself. Architect Jean-Pierre Houdin proposed an alternative, the internal ramp theory. This 3D wireframe reveals the proposed internal path. Houdin suggests the builders used an external ramp for the base, but completed the rest of the structure using a corkscrew tunnel built just inside the outer walls. Another more recent hypothesis suggests the use of a hydraulic lift system, where ancient engineers used water pressure to float the heavy blocks into position. It is likely that the builders used a combination of these methods, adapting their engineering solutions as the structure increased in height. This massive investment of time and labor raises the question of purpose. If the pyramid wasn't a machine, why coordinate 30,000 workers for 20 years? The architecture shows a clear progression from earlier tombs. The step pyramid of Djoser, designed by Imhotep, was created by stacking flat stone structures called mastabas. The Great Pyramid represents the final stage of this long architectural evolution. The choice of location reflects Egyptian religious beliefs. The west bank of the Nile, where the sun sets, was considered the realm of the dead. The ancient Egyptians built the Great Pyramid as a meticulously engineered vessel for the afterlife. Its position on the west bank ensured the pharaoh's soul could depart alongside the setting sun. The primary technological achievement of the Old Kingdom was not hidden machinery, but rather the ability to organize vast populations and systematically exploit the natural environment. Modern science continues to probe the structure. Researchers currently send robotic cameras into narrow, unexplored shafts, finding red symbols painted on the walls and searching for undiscovered chambers. The Great Pyramid forces us to rethink our definition of advanced technology. It remains a testament to what humans can achieve through planning and coordinated effort, standing 4,500 years after its completion.